Hello friends. So welcome to lecture series on multivariable calculus. So in this lecture we will deal with Euler's theorem for homogeneous functions. So what homogeneous function are first? Now suppose you have a function of two variable x and y. Now this function is said to be homogeneous function of degree n if f of alpha x alpha y is equals to alpha raised to power n f of x y. Okay. So then this, if this property hold for a function of two variable f x y, then we say that is a homogeneous function of degree n. Suppose f is x square plus y square. It is clearly homogeneous because if you take alpha x alpha y, so it is alpha square times x square plus y square. You simply replace x by alpha x and y by alpha y. So alpha square will come out and it is alpha square times f of x y. So we can say that it is a homogeneous function of degree 2. Now say f is sine inverse x upon y. It is also homogeneous because if you replace x by alpha x, y by alpha y, so it is sine inverse of alpha x upon alpha y, which is sine inverse x upon y, and it is same as f x y. So it is also homogeneous function of degree 0 because this can be written as alpha raised to power 0. Okay. So it is also a homogeneous function of degree 0. Say you have this function x raised to power 4 plus y raised to power 4 upon under root x plus under root y. Okay. Now this is also homogeneous function because if you replace x by alpha x and y by alpha y, so from the numerator you will be getting alpha raised to power 4 and from the denominator you are getting alpha raised to power half. So it is 4 minus half, that is 4 minus half, that is 7 by 2. So this is homogeneous function of degree 7 by 2. Okay. Now there are some functions which are not homogeneous, like you are having say x cube plus xy. It is not a homogeneous function because when you replace x by alpha x and y by alpha y, from here we are getting alpha cube and from here we are getting alpha square. So the entire alpha is not coming out. So that means this function is not an homogeneous function. Similarly, suppose you have this function sine inverse of x square upon y. It is also not a homogeneous function. Okay. So this is homogeneous function. So and homogeneous function is also expressed as, you see, if we are saying that f is a homogeneous function of degree n, then f can be expressed as x raised to power n some g of y by x, or f can be expressed as some y raised to power n h of x upon y, if it is a homogeneous function of degree n. Now here are some examples. The first example is homogeneous function of degree 2. The second example is homogeneous of degree 0, we can easily verify. The third example is homogeneous function of degree minus 2. The third example is not homogeneous. Now here we have a homogeneous function of n variables. The same definition is applicable for homogeneous function for n variables also. You simply replace x1 by lambda x1, x2 by lambda x2 and so on. If you are getting lambda raised to power n times the same function, that means the function is homogeneous of degree n. Now comes to Euler's theorem. It states that if f is a homogeneous function of degree n in x and y and has continuous first and second order partial derivatives, then these two result hold. So this is Euler's theorem. So let us try to prove this theorem first. So f is a homogeneous function, it is given the statement. So f can be written as x raised to power n g of y by x. So we are assuming f as a homogeneous function of degree n. Okay. Now what will be del f upon del x? It will be x raised to power n, first as it is derivative of second plus second as it is derivative of first. Similarly, what will be del f upon del y? It will be x raised to power n g dash y by x, and this again which is 1 by x. Now, what will be x f x plus y f y? So, simply multiply this by x and this by y and add them. What we obtain? We obtain it is x raised to power n minus 1, because it is x raised to power n minus 2 into x, it is x raised to power n minus 1 with negative sign times y g dash of y upon x plus n x raised to power n g of y by x plus, here when you multiply by y, it is y x raised to power n minus 1 g dash of y by x, and these two terms cancel out, it is n times, and this is nothing but f only, so it is nf. So, we can say that x f x plus y f y is nf. Okay. It is true only for homogeneous functions. Okay. Now, the second result, now we have obtained that x f x plus y f y is equals to nf. Okay. If f is a homogeneous function of degree n. Now, let us differentiate both the side partially with respect to x. When you differentiate both sides partially with respect to x, what we obtain? It is first as it is derivative of second plus second derivative of first plus y into f y of x is equals to n of f x, which is, or it is x f x x plus f x plus y f y x is equals to n f. So, this is say second equation. Now, again you differentiate equation 1 partially with respect to y, both sides. So, what you will obtain? It is x f x y plus y f y y plus f y is equals to n f y. Now, you multiply equation 2 by x and equation 3 by y and add them. Okay. So, what you will obtain? It is x square f x x, from here it is y square f y y plus it is x y times f y x plus it is when you multiply this by y, it is x y times x y plus it is x f x plus y f y, that we can put on the right hand side. So, what we will obtain? It is equals to n minus 1 times x f x plus y f y. Okay. Now, since in the statement it is given to us that it has continuous first and second order partial derivatives. So, we can say that f x y is same as f y x, both are equal, because it is having first and second order continuous partial derivatives. Okay. So, from here we can say that it is x square f x x plus y square f y y plus 2 x y, we can call it f x y or f y x because both are same, and it is equals to n minus 1, and this value is n f. So, it is n into f. So, in this way we obtain the second part of the theorem. Now, say we have the first problem. First problem is u equal to under root y square minus x square sin inverse x by y. Now, sin inverse x by y is a homogeneous function of degree 0, okay, and here it is also homogeneous function of degree 1, because when you replace x by alpha x and y by alpha y, so alpha square will come out from this inside bracket, and under root we are having, so it will be alpha will come out. So, basically the degree of this problem, this function is 1. So, by the Euler theorem we can easily say that x ux plus y uy is equals to nu, and n is 1. So, it is equal to u directly by the Euler's theorem. So, the first problem is over. Now, come to a second problem. Now, for the second problem is also homogeneous. You see, u equal to y cube minus x cube whole divided by y square plus x square. The degree of this function is 1. So, x ux plus y f uy will be equal to nu, and n is 1. So, it is u. And for the second part, x square uxx plus 2xy uxy plus y square uyy, it is equals to n minus 1 into f, and n is 1. So, when you substitute n equal to 1, so this term will be 0, hence the second part, the right hand side is 0. Okay. So, this problem is also over directly by Euler's theorem. Now, let us come to these problems. Okay. Now, the first problem is u is equal to ln x raised to power 4 plus y raised to power 4 upon x plus y. Now, this function is not homogeneous function, because you can simply obtain, because when you replace x by alpha x and y by alpha y, so alpha is not coming out, so it is not an homogeneous function. Okay. And suppose you want to find out x ux plus y uy or x square uxx plus 2xy uxy plus y square uyy. How can we obtain that? Now, this implies e raised to power u is equals to x raised to power 4 plus y raised to power 4 upon x plus y. Now this is homogeneous. Okay. Say if this function is, say, f, if e raised to power u is f, okay, now it is an homogeneous function. So, for homogeneous function Euler theorem is applicable. So, we can simply say that x f x plus y f y will be equals to n f, and n is 3. So, it is 3f. And what is f? F is e raised to power u. So, what will be f x? It is del by del x of e raised to power u, which is del by del u of e raised to power u into del u by del x, and which is e raised to power u into ux. And similarly, f y will be e raised to power u into uy. So, when you substitute these values here, so what you will obtain? It is x, okay, e raised to power u will come out from both the terms. So, e raised to power u will come out, it is x ux plus y uy is equals to 3, and f is e raised to power u, e raised to power u cancels out. So, this implies x ux plus y uy is equals to 3. So, that is how we obtain the first part of the problem. Now, second part can also be obtained. You differentiate partial respect to x both the sides. What you will obtain? X uxx plus ux plus y uyx is equals to 0. Okay. Now, I differentiate partial respect to y both the sides. So, it is x uxy plus y uyy plus uy is equal to 0. Multiply this by x and this by y, add them, assuming these two are equal, uxy and uyx are equal. Okay. So, this implies x square uxx plus y square uyy plus 2xy uxy will be equals to, it is x time ux plus y time uy, that will go to right hand side, which is minus x ux minus y uy, which is minus 3, because x ux plus y uy is 3. So, hence we can obtain that this value is minus 3. Now, come to second problem. For second problem also, if you directly see the problem, the problem is not an homogeneous one. You see, what is the function here? Function is u is equal to cos inverse x plus y upon it is under root x under root y. For x y lying between 0 and 1. Okay. Now, this function as a whole is not a homogeneous function, but if you take f is equals to cos of u, which is equals to x plus y upon under root x plus under root y. Now, f is homogeneous function, f is equal to this, and it is a homogeneous function of degree 1 by 2. So, Euler's theorem is applicable for f, for the function f. So, what will be by Euler's theorem? It is x f x plus y f y is equals to n f, and n is 1 by 2, that is 1 by 2 times f. Now, what is f? F is cos u. So, what will be f x? Again, it is del by del x of cos u, which is del by del u of cos u into del u by del x, and that will be minus sin u into u x. Again, what is f y? F y is del by del y of cos u, which is del by del u of cos u into del u by del y, which is again minus sin u into u y. Okay. Now, when you substitute these two values in this equation, what you will obtain? This is x, f x is minus sin u. So, minus sin u can come out, it is x u x plus y u y will be equals to 1 by 2 times f, and f is cos u. So, we obtain that x u x plus y u y will be equals to minus 1 by 2 cot u. Okay. So, that is how we obtain the first part of the problem. So, what I want to say basically, sometimes the problems are not homogeneous, but we can make it homogeneous by substituting f as some function of u. We can apply Euler's theorem for this f, because this f is equal to this, which is homogeneous, and later on we find f x and f y in terms of u, and then we can simply find the values of x u x plus y u y. Again suppose you want to find out x square u x x plus y square u y y plus 2 x y u x y for this problem. So, you differentiate both sides with respect to x partially. So, what you will obtain? X u x x plus u x plus y u y x is equals to minus 1 by 2. Now, derivative of cot is minus cosec square u, and u again, that is u x. Okay. Now, to differentiate again this equation both sides with respect to y partially. So, what you will obtain? X u x y plus y u y y plus u y is equals to minus 1 by 2 into minus cosec square u into u y. Multiply first equation by x, second equation by y, multiply this equation by x, this equation by y, and add them. So, what you will obtain? We obtain x square u x x plus 2 x y u x y plus y square u y y will be equal to, it is 1 by 2 cosec square u will come out, it is x u x plus y u y, which is minus 1 by 2 cot u. And this u x, x u x and y u y will go to the right hand side, which is negative of minus 1 by 2 cot u. So, what we have to show? We have to show this thing. So, you can take 1 by 4 common. When you take 1 by 4 common, it will be from this side we got minus cosec square u into cot u, and it is plus 2 cot u, and it is equals to 1 by 4 cosec square is 1 by sin square, cot u is cos upon sine plus 2 cos upon sine. Now you take the LCM and simplify. It is 1 by 4. You take the LCM sine cube u. It is minus cos u plus 2 cos u times sine square u. So what you have to show? Cos u into cos 2u. So cos u can come out. It is 2 sine square u minus 1, and this is negative of cos 2u. So it is minus 1 by 4 cos u cos 2u upon sine cube u. So that is how we can prove this part of the problem. Now similarly we can go for the third problem. Here we can assume tan u as fu. So that f, which is x cube plus y cube upon x minus y, becomes an homogeneous function. We can apply Euler's theorem for f, okay, and later on we can take fu as tan u, find fx and fy, substitute in these equations, so that we can obtain the values of a and b part of this problem. Now we have one result for Euler's theorem. Let us discuss this result. Suppose function f is a sum of two functions g and h. This is a homogeneous function of say degree n, okay. This is also an homogeneous function of some other degree, say m, okay. What is given? Oh, g is m and this is n. So suppose this is m and this is n. So suppose f is a function which is a sum of two functions. G is a homogeneous function of degree m, h is a homogeneous function of degree n. Now is f homogeneous? It can be homogeneous if m is equal to n. If m is not equal to n, so f will not be an homogeneous function. So can we apply Euler's theorem for such type of problems? You see, g is an homogeneous function of degree m. So for g, Euler's theorem is applicable. So we can say that x gx plus y gy is equals to mg. H is a homogeneous function of degree n. So for h, Euler's theorem is applicable. So that will be x hx plus y hy is equals to nh. You add the two equations. When you add the two equations, it is x gx plus hx plus y gy plus hy and is equals to mg plus nh. Now if f is equals to g plus h, so what is fx? It is gx plus hx, and what is fy? It is gy plus hy. So we can say that it is x fx plus y fy, which is mg plus nh. So this is basically a consequence of Euler's theorem. Suppose a function can be expressed as sum of two homogeneous functions of different degree, then x fx plus y gy y fy is equals to mg plus nh, where degree of f is g is m and degree of h is n. Similarly this is an homogeneous function. So we can say that x square gxx plus 2xy gxy plus y square gyy is m minus 1 into g, and again this is a homogeneous function of degree n. So x square hxx plus 2xy hxy plus y square hyy will be equals to n minus 1 into h. Now you again add the two equations. So what you will obtain? It is x square gxx plus hxx plus 2xy gxy plus hxy plus y square gyy plus hyy will be equals to m minus 1 into g plus n minus 1 into h. Now, gxx plus hxx from here is fxx plus 2xy, it is fxy plus y square, it is fyy, which is equals to m minus 1 into g plus n minus 1 into h. So, hence we have shown the second consequence of Euler's theorem. Okay. Now, suppose we have the first problem. Okay. So, in the first problem u is equals to this term plus this term. Now, this term is a homogeneous function of degree 2, the first term. The second term is also an homogeneous function of degree 1. So, both are homogeneous function having different degree. It is a homogeneous function of degree 2, it is a homogeneous function of degree 1. So, if you want to compute x ux plus y uy, so we can directly apply the first consequence of Euler's theorem, that is mg plus nh, where what is m here? M is 2 and g is the first term plus n is 1 into second term. So, the answer of the first part will be, first is x ux plus y uy will be, the first term has a degree 2. So, it is 2 times g is the first term, is it okay, plus the second term has a degree 1, that is n into h, n is 1 and h is x sin inverse y by x. So, this is the value of the this expression. Now, the value of second expression, which is x square uxx plus y square uyy plus 2xy uxy will be equal to m minus 1 into g plus n minus 1 into h. That is simply 2 x raised to power 4 plus y raised to power 4 upon x square plus y square. So, that is how we can solve this problem. Now, suppose you want to solve second problem. Okay. In the second problem, this is not homogeneous, however, this is homogeneous. Okay. The second is u is equals to e raised to power x square plus y square plus, it is x square y square upon x plus y. Suppose it is g plus h. H is clearly homogeneous of degree 3, but g is not an homogeneous function. So, g is e raised to power x square plus y square. So, you can make ln of g is equals to x square y square. Now, this capital G is an homogeneous function of degree 2. Okay. So, now we can apply the consequence of Euler's theorem on capital G and H. Okay. So, we can say that x gx plus y gy will be equals to 2g. Okay. And what will be gx from here? It is 1 by g times 1 by g can come out, x gx plus y gy will be equals to 2 ln g. So, this implies x gx plus y gy will be 2g ln g, and for h it is x hx plus y hy will be equals to 3h. Now, you add the two equations, it is 2, it is 1, you add the two equation. So, what you will obtain? It is x times gx plus hx, which is ux, okay. Y times gy plus hy, which is uy, is equal to this plus this, and hence x ux plus y uy, which is equal to 2 times x, g is e raised to power x square plus y square, log g is x square plus y square this side, plus 3h, h is so that is how we can find out the value of this expression. So, thank you very much.